organizer for giving me this opportunity to present our work. So today I'm going to talk about the patterns of non-redundancy, primary beam non-redundancy in closed pack interferometers. This work has been done with Phil and Hugh. So, a little bit of introduction. 21 centimeter signal is an important tool to study the high redshift universe. The upper panel shows the evolution of the 21 centimeter signal as a function of redshift of cosmic time. And you can see there are some large scale structure which can be probed uh, using the 21 centimeter signal detection. Lower panel shows the power spectrum at a different length scale. So using this 21 centimeter signal at different epoch, we can probe the evolution history of the universe at different as a function of cosmic time. But the challenges are that foregrounds are much larger than the expected signal. So the radio interferometers which are being used to detect the 21 centimeter signal have to be calibrated precisely for this detection, and this is the calibration precision is should be of the order of 10 to the minus 5 to detect the 21 centimeter signal conclusively. Redundant calibration is one of the method where we measure the sky signal uh, at different pair of antennas multiple times so that you can reduce the noise using this same sky signal measuring repeatedly, and also you can solve the antenna gains by using this redundant calibration method, and this techniques is adopted for the Hira interferometers. But the problem is that still it is not perfectly redundant. There are some deviations which I will explain later. There are other realistic uh, patterns or realistic effect where the interferometers is not perfectly redundant. Here the y-axis shows the measure of decoherence, or which basically the measure of non-redundancy as a function of the time time of observation, basically LST range. And you can see that if it is perfectly zero, means your array is perfectly redundant. But apart from zero, there are some non-redundancy present in the data, and you can see that it is less than 5% for different types of baseline length, different redundant group baseline length and angle. So some level of non-redundancy is present in the data. So there are various reasons is uh, mm, which introduce some non-redundancy. Basically, the feed position, the receiver, the feed position is rotated or misaligned, or some other can be can introduce some non-redundancy. And also the primary beam patterns of the different antennas might be different, so that uh, we have started later. And positional errors, so these two pairs of antenna might be at the same separation, so there are various reasons due to that your array is not perfectly redundant. So what is the effect? The left panel shows the simulations of the Hera observations, Hera interferometers, and the left panel shows how there is no non-redundancy present in the data. And you can see that the foreground, which is the smooth behavior as a function of frequency, reside only in the wedge shape region here, and the upper region is dominated by the 21 centimeter signal or noise. In the middle panel, it shows the same thing, but there are some non-redundancy due to position error or beam error. And you can see that the region which or the 21 centimeter signal dominates is decreased, or it is as compared to the left panel. So basically, the area of the measurement 20, of the 21 centimeter signal can be reduced due to the various effects, due to the non-redundancy. Basically, the foreground power can leak from the OH to the UR window. So that is the effect of the 21 effect of the non-redundancy, and it has it has been shown. It has shown in this paper. So in this work, our aim is to study the effect of primary beam for the Hera array. And we have studied different types of primary beam in our simulation and how it affects the measurement. So this is the left panel shows the primary beam of different types of non-redundancy. The black solid line shows the uh, perfectly redundant primary beam, which is the same for all antennas. And this is taken from this paper, the analytic simulation of the Hera beam, and we fit some polynomial, and you can see that you see, and we have used this as a perfect model of the primary beam. On top of that, we have introduced some non-redundancy. So basically, the red line shows the side lobe perturbation, how the main lobe is same, but side lobe is different for the different antennas. The position and the level of side lobe perturbation is different. The blue line shows the main lobe, how the width is different for the different antennas. The stretch is how the all the the primary beam shape is stretched with respect to the true one. So when we have introduced at different level for the different antennas, means which is not the same for all antennas, and introduce some non-redundancy in the array. In the right panel, we are showing how the beam is the elliptic beam, not a symmetric as a function of uh, azimuth angle. And we introduce some elliptic beam which is asymmetric, and also we have introduced rotation in the elliptic beam. So these are the different types of primary beam non-redundancy we have introduced in our simulations. Next, we use a small array, 10 number of antennas to simulate the divisibility data. And this is the small number we choose because it is computationally much faster, and also we are starting the primary beam non-redundancy, non any baseline dependence, so that's why this is sufficient for our study. Next, we introduce some point source model. We have used the Gleam catalog, and there are some blank region in the Gleam survey, but we filled this position from the we from this blank pixel we fill from the field region, and we introduce some modified catalog for the Gleam survey, and we use this in our simulation. Also, we have added a diffuse sky model, the GSM sky model, for the diffuse part. And also we add some system noise based on the autocorrelation of the visibilities, and also introduce some band pass. So these are the total simulation setup, and we repeat the simulation for this 100 to 120 megahertz, and this is the LST range, and we whole things we are doing for the Stokes eye, means we are not doing any polarization leakage or this kind of study, whole thing for Stokes eye. Analysis part, we have used Hiracal for the calibration, redundant calibration. So we have introduced non-redundancy due to the various primary beam pattern, and we are analyzing. Basically, we are calibrating the data using redundant calibration method. So there should be some error, and also we have find some outlier which are removed and replaced with the mean of the nearest neighbor points. And there are some degeneracy in our simulations, basically the redundant solution, which is solved using the true gains. And finally, we use here spec for the power spectrum measurement. The results I want to show is the antenna gain, the difference of the antenna gain with respect to the true one for different types of non-redundancy. Here, each panel shows different types of non-redundancy we considered, and the difference of the calibrated gain with respect to the true one, which was introduced for the simulations. The upper panel shows the relative sky brightness temperature, basically the visibility autocorrelation, which measures the sky brightness. And you can see that the difference, basically the error in the gain solution is maximum in this 13 to 14 LST range hour, where the brightest source sen A is within the main lobe in our simulation. So that is the fact that the gain solutions or the redundancy calibration is more, it is the gain solution is mm, a, mm, the difference of the gain solution is much larger with respect to the true one when the brightest source is within the main lobe. So that is the antenna gains for one antenna, but we have seen these features quite true for the other antennas also. Next, we show the visibility variance for a perfectly one redundant group 14.6 meter and storage direction. The y-axis shows the variance of the visibility and x-axis is the LST range. And what we expect if there is a perfect redundancy, it should be a noise like, which is the case for. So different rows shows different types of non-redundancy, side lobe, main lobe, elliptic beam, stretched, and each column shows different types of foreground. The left panel shows the point source and diffuse in our simulations. In the middle panel, only the point sources are present. In the right panel, we have shown the point sources but without bright sources. And you can see that it almost like a noise like. But in the middle panel, when there are no bright sources in our simulation, it is almost a noise like. But when the bright sources are present in that, basically the same A in our case, the 13 to 14 hour, the brightness, the variance of the visibility increases. So basically due to the due to the brightest source in our simulations, the variance of the visibility increase in this LST range. In the left panel, when the diffuser present, we are seeing that it is almost noise like, but the noise level is increased due to this diffuse pattern. So this is the conclusion is that the same, the visibility variance increase or the error in the visibility is increase when the bright sources are present, due to the non-redundancy effect is more when the bright sources are present. Next, we want to show the decoherence, basically the difference of the coherent power spectrum minus the incoherent power spectrum. And for a perfectly redundant case, it should be zero. If it is not redundant, there should be some variations in delta chi. So here we are showing the delta chi as a function of LST for different non-redundancy type. And you can see that it changes. So for the upper left panel, it is perfectly zero when it is no perturbation, no perfectly redundant. But for other cases, it has some value, basically 2.5% error. And it depends also on the angle of the baselines and also length of the baseline. So this is for the point sources, and you can see that the error is 2.5% at that LST range when the same is within the main lobe. For other, so the next I am showing the point sources plus diffuse is added in the simulation. The features is quite similar. At that LST range 13 to 14, it is maximum, and now the error increase due to this diffuse, which is 10%. So there are also some other features in that 30 in the 15 to 16 LST range, where the galactic center is rising. So these are the results I wanted to show. The summary is that precise calibration is required to detect the 21 centimeters signal, and redundant calibration is one of the method for the calibration. But the various real-world imperfection in the array result in deviations from the perfect redundancy. And we have studied the various type of primary beam non-redundancy which can occur in the real observation, and we have studied the effect, and we see that the visibility variance and the gain solution difference is maximum. Basically the effect of non-redundancy is maximum when the brightest of point sources are within the main lobe, and also the level of decoherence, basically ultimate the decoherence is maximum or less than 10% when the brightest sources is present. So these are the results I wanted to show, and thank you.